Hi, grade 8. This is day 27, page 559, numbers 9 through 39, the odds. I'm going to do things a little bit differently today. We're going to take a look together at pages 556 and 557. We're going to talk about some of the things we see there as best as we can, and then we'll let you move on to the assignment. I don't think you're going to find this too hard, but there are a few things we need to make sure you understand. Starting on page 556, it says that we're talking about three-dimensional figures. What in the world does that mean? Three-dimensional figures are figures that have a width to them, a height to them, but they also have a depth to them. Okay? If I draw, for example, a line and put dots on the ends of the lines instead of arrowheads, that is a line segment. That is not a three-dimensional figure. All that has is two dimensions. Actually, maybe just one dimension, excuse me, because all it has is length. It doesn't have width. It doesn't have height to it. However, if I take that line segment and I turn it into a triangle, now that triangle has a width to it and it has a height to it. This would be a two-dimensional figure. If I then take and draw some more dots, say here, here, and I connect this in with this and that with that, and then I put a dot, let's put a dot, how about right about there, and we draw in some dotted lines. Now, we've got a three-dimensional figure. That's pretty ugly. But it's got width, it's got height, but it's also got depth going away from us. So that would be an example of a three-dimensional figure. Three-dimensional figures, length, width, and height. We can do that same thing with, say, for example, something like this cylinder shape. Pop can or something of that nature has height to it, it has width to it, but it also has a depth to it. Okay? Underneath, it talks about a couple of yellow terms that we need to make sure we're aware of. Look at the word plane. A plane is a two-dimensional flat surface that extends in all directions. It's kind of hard to visualize a plane, but for example, this whiteboard is a plane. If we think of it as going in all directions, vertically and horizontally, it doesn't have depth to it, at least in this particular case. They talk about something called a polyhedron. It says intersecting planes can form three-dimensional figures or solids. A polyhedron is a solid with flat surfaces that are polygons. Well, what do we mean by a polyhedron there? Well, when we go back to drawing, say, for example, that cylinder, this would not be a polyhedron. Why? Because it doesn't have flat surfaces throughout it. It has a flat surface on the top, the circle, another flat surface on the bottom, the other circle, but the curved part around the outside, that would not be a flat surface, and so this is technically not a polyhedron. However, if you look at the bottom of page 556, they drew a cube, and that would be an example of a polyhedron because it's got all flat surfaces. Okay, that's a polyhedron. Then they have three more terms there: edge, vertex, and face. Edge, vertex, and face. What do they mean by an edge? An edge is the line segments that are on the outside of this polyhedron. The vertexes are the points on the outside of this polyhedron. And finally, what's the other one? Face, that's any of the flat surfaces themselves. So what can we say about a shape like this? We can say a lot about it. When we look at this, I would call this a prism. What kind of prism? Well, we could call it a square prism. We could also call it a rectangular prism. It depends on whether or not we know if all of the edges have the exact same length. It appears as if all of the edges have the exact same length, but we're not positive based on the way this is drawn. So it might be a square prism, and it might be a rectangular prism. The next question I might have is, do we know how many edges this particular shape has? And my pen is dying. Let me see if I can find another one. How many edges does this thing have? And we could talk about 1, 2, 3, 4. 4 on the front. 5, 6, 7, 8, 9. Boy, this is kind of hard to count, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got 12 edges. I think I've got them all. 4 in the front, 4 in the back. 1, 2, 3, 4 around the top and the bottom. So that makes 12. Yep, 12 edges. How many vertexes are there? But the plural of vertex isn't vertexes. The plural of vertex is the word vertices. How many vertices do we have? That would be those dots, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 in this particular case. How many faces do we have in this particular shape? Well, the front face, the back face, the two sides, and the top and the bottom, that makes a total of 6 faces. Now, what if we were asked to identify the names of some of these concepts here? Well, in this particular case, it'd be kind of hard to do because I haven't given any names to any of the vertexes. So let's do that. Let's call this L, M, N, O, P, Q, R, and S. I've given every single vertex a letter name, and now let's see if we can identify all of the edges. All of the edges. Well, let's start in the front. How about line segment LM? That's definitely an edge. How about SR? That's an edge. SL, that's an edge. RM, that's an edge. So I've done 4 of them so far. In this case, I did the 4 in the front. I need a total of 12. Let's do, how about the back? OP here. How about ON? There we go. How about NQ? And how about QP? So that's 1, 2, 3, 4, 5, 6, 7, 8. I need 4 more. How about the side ones? SP? How about LO? How about MN? And finally, how about RQ? Line segments. We've got 12 different line segments listed here. These are the edges of this particular shape. What about the vertices? Well, that's a little bit easier to name. The vertices, we just name them according to their dots, right? And so in this case, the vertices are L, M, S, R, P, Q, O, and N. All 8 of the vertices right there. How about the faces? The faces. Well, how do we name faces? We're going to name them with 4 letters each. I got 6 faces here. The front face, I'm going to call that SLMR. And then the back one, how about PONQ? How about the top one, SPQR? How about the bottom one, LONM? So I've done what? 4 of them. I need 2 more. How about the side one on the left side, SLOP? Ooh, slop. And the side one on the right side, RMNQ. Now there's one other concept that you might find yourself being asked for in this. The concept of bases. Look at the top of page 557. They're trying to talk to you about the difference between something called a prism and a pyramid. If you remember, we called this a prism. Why is it a prism and not a pyramid? When I think of the pyramids, I think of the Egyptian pyramids at Giza and such. And how to identify what those are. They're these huge blocks of stone, multiple pieces of stone, millions of pieces of stone, and they all come together at the top in a point, and the faces all around are triangles, but then they have a base it sits upon, and that base is apparently, in the case of the Egyptian pyramids, some sort of square. And they talk about that in the paragraph on the top of 557. They say that prisms have two bases, while pyramids only have one base. So look at that table on the top of 557. Do you see the triangular prism and the rectangular prism? They call them prisms because they have two bases, the top and the bottom faces. But in the case of the triangular pyramid and the rectangular pyramid, those are called pyramids because they only have one base. The one base is a triangle or a square or a rectangle, and then all the faces around the side of it are triangles so that it forms in that distinctive point shape. Study example 1 on the bottom of 557. I think you'll find it's pretty similar to what we did up here. And then let's move on to page 558. 558 is talking about something called skew lines. What in the world is a skew line? Well, we know that sometimes lines intersect. And we know that sometimes lines are parallel to each other, right? Let's show examples of that. On this particular shape, if I were to draw SR as a line, SR is parallel to line LM. They're parallel lines. But if I talk about SR and I think about line RM, those would be intersecting lines because SR would go right through the middle of RM if we turned them both into lines instead of line segments, right? But what if we could find two line segments that are not parallel and do not intersect? That's the idea of skew lines. That's what they mean by that. So if we look carefully here, look at SR and look at OP. You see those two? If you can imagine SR going forever and ever in both directions, and if you can imagine OP going forever and ever in both directions, those two would never meet, and they wouldn't be parallel. And those two would never meet, and they would never be parallel. I think there was a glitch in the system, so I just want to rephrase that in case we missed this. SR and OP, those two line segments, if we turned them into lines, they would never meet, they would never intersect, and they would not be parallel to each other. And that makes them skew lines. So that's what they're talking about up there. Let's see. Do we know what a diagonal is in the case of one of these polyhedrons or these prisms and pyramids? If we look up here, a diagonal would be, for example, PM. That would be an example of a diagonal. Another diagonal would be LQ. Another diagonal would be SN. Got to put the line segment symbols on there. And how about RO? That would be another diagonal. Do you notice how, for example, LQ starts here and goes through the middle of the shape to reach that point that's opposite and above it? If we talk about, say, for example, PM, PM's at the top, back, left, and M is at the bottom, front, right of this shape. And so that would be an example of a diagonal as well. Study example 3 on your own. Keep in mind that we're not going to be working with isometric dot paper today at all. Your assignments starts at number 9 and goes to 39. And if my memory's right, I don't think you're going to find that they're going to make you draw on isometric dots paper, if my memory is right. There is problem 29 where they ask you to look for the two figures that have the same dimensions, but I'm thinking you can probably figure that out. Anyway, if you have any questions, feel free to give me a call. My phone number is, of course, 517-242-3138. Thank you, ladies, and have a good day.